Welcome to the course on computer design of electrical machines. We will have a lecture 10 today on the design of DC machine part 2. So, today outline of the presentation of today lecture is estimation of various design parameters, design of armature and design of commutator and brushes and design of field system of DC machine, then followed by exercise, numerical problems and references. So, coming to first starting from in DC machine, the number of pole selection. The number of poles, of course, in AC machine is fixed by frequency and speed by relation Fp equal to 120 F by 120 F by N. And where the typically depends on your, of course, here depends on frequency. Here depends on weight of iron parts, then weight of copper, length of commutator, labor, flashover, and distortion of the field. So, however, only a small range of poles is economically suitable for DC machine, and the factor that govern the choice of number of poles are listed here. First is the frequency. The frequency of reversal of induced voltage is given F equal to Pn upon 120. When the number of poles increases, the frequency becomes high, increasing core losses. Lower value 25 to 35 Hz frequency should be used for large machine, and higher frequency in the range of 50 to 75 may be used in a smaller DC machine. Now, coming to the weight of the iron parts. So, first is the yoke. So, for two pole machine with the phi as a flux per pole, the yoke carries half of the flux pole pi by 2. If the number of poles increases to 4, the flux per pole changes to pi by 4. So, here the By equal to pi by 2, and that is a cross section area of the yoke, that is Ay. So, it becomes pi upon 2 p Ay, or proportional to 1 upon P into Ay. So, if the number of poles are double, the yoke flux reduces to half. By keeping a yoke flux density the same, Py is almost constant, the weight of the iron in yoke decreases proportionally as the yoke area decreases. So, typical example you can see here from 2 pole to 4 pole, the flux in the yoke reduces of corresponding to that, like comparatively. And now coming to typically of your armature core, the flux per pole divides into two parallel paths in the armature core. So, for the two pole machine, the flux in armature core is pi by 2, where the 4 pole is pi by 4. Hence, the increasing the number of poles not only decreases the armature flux, but also increases the frequency of flux reversal in the core. So, increasing frequency increases the core loss. Now, typically for two pole machine, since the flux carried by armature is pi by 2, so eddy current loss in the core is eddy current proportional to B square F square, or proportional to pi by 2 into AC square or into F square, or proportional to pi T upon 2 PAC into Pn by 120 square. So, therefore, eddy current loss in the armature independent of the number of poles. Now, coming to hysteresis loss in the armature core, so hysteresis loss is F into B to power 1.6 flux density in the core, that will be proportional to pi T upon 2 PAC square into Pn upon 120, and that is proportional to 1 upon P to power 0.6 into A to power AC to power 1.6. So, where the AC is proportional to 1 upon P to power 0.6 to 1 divided by 1.6. So, you can call it decreases as the number of poles increases for a given hysteresis loss, and thus the weight of iron used in the armature core reduces as the number of poles increases. Now, this is a typically comparison between the two pole and four pole machine as far as eddy current losses are concerned. In the two pole machine, how it is relating to the flux like or so. And comparison between two pole machine for hysteresis loss, here also you can see the comparison like how it is really related to the number of poles. Like. So, now coming to armature copper or weight of the copper. So, the armature ampere turns ampere conductor per conductors are independent of number of poles. So, total weight of the active copper does not vary with the number of poles, because all the slots have to be filled properly with the copper. So, total weight of the active copper does not vary with the number of poles, but the inactive copper, that is copper at the overhang, decreases as the number of poles increases. That is the overall length of the copper and overall length of the machine reduces. As you can see, as you see the number of poles increases, so you can have a pole pitch decreasing, and that is the reason you can clearly see that in lower part of this the overhang portion is reduced, like compared to the length of BCD, the length of BFG is lower. So you can call it like a weight of the copper for this winding. For a given length of the coil, the overhang goes on reducing as the number of poles increases. As the overhang length reduces, the weight of the inactive portion or a inactive copper portion is used at overhang also reduces. So overhang is proportional to 4 pitch in bracket pi d upon P. And armature winding of 2 pole, you can just see clearly here the happen. Now coming to weight of the copper in field winding, the field copper, since the field ampere turns are fixed, so with the increase in the number of poles, the field ampere turns per pole reduces and the area of the cross section of per pole also reduces. Now coming to the length of the commutator, for the lap winding with the P equal to 2, the current path in armature 1 by 2, I by 2, and then the current per brush field is also I. Now coming to this length of the commutator for lap, the P equal to 4, so current in the parallel path is I by 4 and the current per brush arm is I by 2, as you can see in the diagram. So now coming to typically the D, length of the commutator, the current brush arm is 2I upon A, or you can call it 2 into number of parallel path, and that give you the brush area AB equal to 2I upon A sigma B, or 2IA into P sigma B, that is equal to 1 proportional to 1 upon P. So it reduces as the number of poles increases. So from the above equation, we observe that the current per brush arm decreases with increase in the number of poles for the lap winding. Now coming to the length of the commutator, since the thickness of the brush is decided on the number of commutator segment, the length of the brush arm and therefore the length of commutator decreases with the increase in number of poles. So AB, that is the area of the brush, equal to thickness into the width and number of the brushes, that TB WB into NB, and the TB held constant from the commutation point of view. So WB NB reduces as the AB reduces, and the length of the commutator equal to LC equal to in bracket WB NB plus clearances reduces as the AB reduces or P increases. Now coming to the labor typically cost, as the induced EMF equal to P phi Zn upon A, and E is proportional to Zn upon A, that is P phi is a constant for a given DC machine, and E proportional to Zn upon P, so for lap wound machine. So for a constant induced EMF with the increase in the number of poles, the number of armature conductors is proportional increase. So now for the large number of poles, the larger armature coils are to be wound, insulated and soldered to the commutator, so labor charges will increase. And for large value of poles, the greater number of field coils are to be wound, which further increases the labor. So now coming to flashover between the brushes, if the number of poles are increased, then the number of brushes will increase. As the number of poles increases, the voltage between the segment increases. So EB equal to voltage between the positive and negative brush and divided by number of segment per pole. As you can see how it is really typically the kind of you can see flashover type. Now because of the increased value of EB and carbon dust collected in the space where the mica is undercut, chances of arcing between the commutator segments are increases, and the arc between the segment in turn may bridge the positive and negative brushes, leading to a dead short circuit of the armature or flashover. Now coming to distortion in the field, so we know the armature EMF turns per pole is AC pi d upon P, and with a smaller number of poles, armature ampere turns per pole increases, and because of this armature reaction, increase armature reaction, the net field is more distorted. Also, sparking of the brush also may be more. The effect of the number of poles on the overall diameter: when the number of poles is less, the flux produced by armature is more, and this reduces the mutual flux in the air gap. So in order to maintain constant value of air gap flux produced by the field or the field ampere turns must be increased. So this calls for more field coil turns and size of the coil defined in the depth of the coil df and height of the coil hf increases. In order to that the temperature rise of the coil is not more, depth of the coil is restricted. Therefore, the height of the field coil increases as the size of the field coil or the number of turns of the coil increases. Now coming to effective number of poles on the overall diameter, as the pole height is proportional to the field coil height, the height of the pole, and hence the overall diameter of the machine increases with the increase in height of the pole. So obviously, as the number of poles increases, the height of the poles and hence the overall diameter of the machine decreases, as you can see in case of the two cases. So now coming to advantage, disadvantage of higher number of poles. Advantage are weight of iron is reduced, cost of the copper in the field and armature is reduced, and overall diameter and length are reduced, length of commutator is reduced, and distortion in the field is also less. And disadvantage, iron loss is more, flashover between the brush arm increases, cost of material increases, cost of labor also increases. Hence, the choice of number of poles has to be judicially made considering all these above factors. So now guideline for the selection of poles is keep the frequency of flux reversal F equal to Pn upon by 2 as should be in between edge 25 to 50 Hz. Current in parallel path Iz equal to I upon A must be limited to 200 ampere. Current per brush Ib equal to 2 Iz must be limited to 400 ampere. And ampere turns ampere MF per pole ATA, that is IZ upon 2P or AC pi d by 2P or equal to AC upon by 2 pi d by P or small AC by 2 into tau must be limited to 12,500, and where T is the polar to pole pitch ratio. So value of ampere turns per pole for various rating of DC machine is given here in the table. So up to 100 kilowatt, this should be less than 5000 ampere turns, and when it is above 1500, it should be less than 12,500. Like so, it's a range of 500 to 12,500 ampere turns. Now, typically, generally used number of poles of the rated power and speed is given here in the table. So if you have a less than 2 kilowatt, normally we have a number of poles 2 and speed in RPM more than 12,000 RPM, and if we have a machine typically of 5 megawatt or 5000 horsepower, that number of poles is 40 to 24, so we can go typically speed up to 375 RPM. Now coming to the estimation of length of air gap in DC machine. The air gap length LG may be estimated by the following empirical relation. So MF required for air gap in cylindrical machine can be expressed as ATG equal to 8,000 square in 800,000 BM Kc into sigma, where Kc is the gap contraction coefficient having a value of about 1.15, and sigma is the air gap length at the center of pole, and BM is the maximum flux density air gap, that is B correction divided by 5. MF per pole will be ATA, that is AC tau P by 2 or AC pi d upon 2P. So value of air gap MF is usually between 0.5 and 0.7 of armature MF, or you can call it ATA will be equal to 0.5 to 0.7 into ATA, and that is equal to 0.5 to 0.7 into small AC into pi d by 2P. So you can call it from these equations, the length of air gap will be equal to 0.5 to 0.7 AC pi d upon 2P into 800,000 into BM Kc. The air gap length of at the pole tip is generally 1.5 to 2 times the air gap length, minimum air gap length. So maximum air gap length will be 1.5 to 2 times delta. Now coming as the design example 1, estimation of main dimension, number of poles and the length of air gap. The question is determine the main dimension, number of poles and length of the air gap of 620 kilowatt 900 RPM generator. Assume the air gap flux density 0.6 Weber per meter square, ampere conductor per meter 35,000, and the ratio of the polar to pole pitch is 0.75 and the efficiency is 91%. The following are the design constraints like peripheral speed should be less than 40 meter per second, frequency of reversal 50 Hz, and current per brush arm is 400 and the armature MF per pole is 7,500 ampere. So required gear be 50% of armature MF and game contraction phase 1.15. Now coming to the solution with the output coefficient C0 equal to pi B average AC into 10 power 3, putting the value it comes to 207. Now power developed by the machine is your PA equal to kilowatt divided by efficiency, so 600 by 0.91, that is 60 kilowatt, and speed N in RPS is speed in RPM divided by 60, that is 115 RPS. So D square L will be P0 divided by C0 N, putting a value it comes 0.2126 meter cube. Now coming to the number of poles, the choice of number of poles for this size of the machine lies between 4, 6 and 8. So comparing the result, typically taking the frequency of the flux reversal, that is Fpn by 2 Hz, and frequency is 30 Hz for 4 pole and 45 6 pole and 60 Hz for 8 pole. Therefore 8 pole cannot be used as the frequency exceeds the 50 Hz. So that I mean, here the power is already, we got 660 kilowatt. Now current per brush we can calculate from this, I mean, voltage and power rating. So IA equal to PA divided by voltage. Armature voltage is come 1200 ampere, and current per arm will be P equal to 4. So IB will be 2 I upon P, that comes 600 ampere. P equal to 6, IB equal to 2 I upon P, becomes 400. So current burst per arm should not exceed than 400. So this means more than 4 pole cannot be used in this machine. So therefore number of poles is taken 4. So now L upon psi tau equal to 1. So L equal to 0.75 into pi d by 6. So it becomes your L becomes 0.393 D. So keeping a value in output equation, 0.393 D cube is 0.2126. So D comes equal to 0.815 meter. So taking a diameter now, D equal to 0.815 meter and length is L equal to 0.33 meter. That is the main dimension of the machine. Like now peripheral speed we have to check. So V equal to pi D N, putting the value it comes 37.7 meter per second. So speed is within the specified limit. And armature MF typically in, for that we have to get pole pitch, tau equal to pi d upon P, that comes 0.42 meter, and ampere turn MF now comes 80 equal to small 80 into tau by 2, so it comes 7350 ampere. So this is also within the specified limit. Now length of the air gap, so maximum flux density in the air gap is B is equal to 0.6 upon 0.75, so it is 0.8 Tesla, and MF required for air gap will be 8 is equal to 800,000 into your B into 1.15 contraction factor into Lg, so that comes like 736,000 Lg, and from this MF is typically for TG equal to 0.5 times 88, so it comes 3675. So from here we can get the value of Lg, that is ATG upon 736,000, so it comes around 5 mm. Now coming to the design of armature. So design of the armature typically involve the determinants of parameter as shown in the diagram also, like number of armature conductor, armature winding, number of armature coil, number of armature slot, design of armature conductor, slot dimension, depth of armature core, and armature resistance. So now coming to typically with the number of armature conductor, number of armature conductor is estimated by following two methods. Method one is we know that mean induced EMF in the conductor is Z equal to B average LVA, where VA is the pi d n, the peripheral speed. So generated induced EMF in armature equal to VA plus IRA for generator and P minus V minus IRA for motor. So V is the terminal voltage and IRA is the resistance, armature resistance drop or voltage drop. So assuming IRA equal to 2 to 2.5% of the V for machine with 500 volt rating, and more than IRA is 5 to 10% for a small machine of with 250 volt rating. Now coming to number of armature conductor. So for simplex winding, since the number of, which is normally normal machines as well as low rating, since the number of path equal to number of poles, so ZC represents the total number of armature conductor per pole. So for simplex wave winding, the ZC represents the half of the total number of conductor on the armature as the number of poles 2. So number of conductor in series is ZC equal to EZ upon E upon EZ. Now that is one method, and second method is the number of armature conductor equal to Z equal to E upon 5 PN, where specific electric loading is AC IZ upon IZ into Z upon pi D, and number of armature conductor is Z equal to AC pi D upon IZ. So you can call it from the slot capacity ZS. ZS will be Z number of armature conductor divided by S number of the armature slot. The number of armature conductor will be Z equal to ZS into S. Now coming to armature winding, the multiplex winding and simplex winding are used in the DC machine. In case of multiplex winding, equalizer connections are being used, which increases the cost of the machine. So simplex windings are generally preferred in the armature of DC machine. So coming to, there are two types of simplex winding: simplex lap winding and simplex wave winding, and as you given in this table below. In case of simplex lap winding, number of parallel paths are 2. Current in each parallel path is 1 upon P of the load current. EMF is E, total number of conductor per large, and current because there are large voltage only, and the total number of conductor large. Current per path is less conductor cross section area, equalizer connections needed, more expensive machine, and generally not no used for a small machine. So however, wave winding, normally number of parallel paths are 2, current in each path is 1 by 2 into full load current, induced EMF in 2 parallel path is E, total number of conductors is less, and current per path high cross section area, and the equalizer connection not needed, and generally used for a small machine. So coming to number of armature coils, so total number of armature conductors is equal to Z equal to P into ZC for simplex wave winding, or Z equal to 2 into 2ZC for simplex wave winding. The number of armature coil will be Z by 2 for single turn coil, and Z upon 2 TC will be for multi-turn coil. That TC is the number of turns in one coil. So now coming to number of armature coils, so number of commutator segments equal to number of coils, and voltage induced between adjacent commutator segment and no load. So EC is the voltage induced per conductor into number of conductor between parallel between adjacent commutator segment. So that is equal to E small ez into 2 into number of turns between the adjacent commutator segment, and that is Z into 2 into number of turns per coil into number of coils per segment on no load. So a capital EC equal to 2 Ez into TC into NC. So that's a capital EC equal to 2 Ez TC NC, substituting Ez equal to BA L VA. So maximum voltage induced between the adjacent commutator segment on no load is E CM equal to 2 BG LA VA TC to NC, where B average is BG at no load. So maximum voltage induced between commutator segment adjacent commutator segment is E CM 1 equal to 2 into 1.3 BG L VA TC NC. BG on typically on load 1.3 times of your BG at no load. So now coming to the max number of armature coils. So maximum voltage induced between adjacent commutator segment equal to on load is equal to ECM1, that is equal to 2 into 1 by LV and 3 inch NC, and that is ECL equal to 2.6 BG L VA TC NC. Substituting psi equal to 0.68 in the this equation, so we get EC1 4 B average L VA TC NC, and substituting VA equal to pi dn, so it becomes EC equal to 4 B average L pi dn TC NC. So substituting the B equal to pi d P phi upon pi dl, so ECL becomes 4 B average L pi d dn TC NC, and ECN we get the 4 P pi upon pi dl into ln into dn into TCLC, or equal to 4 P phi and TCNC, or 4 P EA upon Z Pn into NC TC NC, and or equal to 4 EA upon Z into TCNC, or EC1 equal to 4 EA upon 2C TC into TCNC. Now the number of armature, that's a ECA now becomes ECL equal to 2A upon C into NC. Add minimum number of armature coils C minimum equal to 2 A NC upon each coil. So for lap winding we know that A equal to P, so using NC equal to 1, so ECM becomes 30. So minimum number of coils will be Q minimum will be 2A NC divided by ECN, that is 2E to P into 1 divided by 30. So EP upon C minimum is EP upon 15. And for wave winding we know A equal to 2, so choosing NC equal to P by 2 and CN 30. Minimum coils is your again Q minimum 2A and NC upon GCL, so that's a 2 EP by 2 into 2 on 30, that's EP upon 50. So hence the minimum number of coils remain the same irrespective of whether machine is lap winding or wave winding. Now coming to again for number of armature coils, so ECL equal to 4 B average LVA TCNC, so EC becomes 4 EZ TCNC. So substituting ECN equal to 30 in this equation, so EZ comes 30 upon TC into NC, or 7.5 divided by TCNC. So now coming to armatures, number of armature slots, the factor affecting the choice of number of armature slot given here. The factors are flux pulsation, cost, cooling, tooth width, and commutation. So coming to first A as a flux pulsation, so flux pulsation give rise to the eddy current losses in the pole shoe and produce the magnetic noise, and these pulsations are produced due to the change in air gap flux because of change in the air gap reluctance due to slot and pole phase, etc. To avoid flux pulsation, the following selections are to be made. So number of the slots per pole will be integer plus 1 half, and number of slots per pole are so will be integer by half. So in actual design it may not be possible to fulfill both the conditions. So in such cases number of the slot per pole should be an integer within the slot per pole equal to the integer plus 0.5. So now coming the selection for armatures based on the cost of the punching of slots or cost of the slot insulation increases with the increasing number of slots, and for the cooling, for large number of slots, the number of conductor slot will be lesser and hence the better ventilation is produced. Coming to the now commutation, so large number of slots and a smaller number of conductors per slot are the better for commutation point of view, and for better commutation, number of slots per pole should be chosen in the range of 9 to 16. Now coming to tooth pitch, tooth width, the slot pitch reduces with the large number of slots, so slot width will also be lesser. The flux density at the minimum section of the tooth increases, which increases the iron losses. Also, it is difficult to support the teeth at the ventilating duct without obstructing the ventilation. The choice of the slot pitch will be tau is equal to pi d upon s and should be in the range between 2 and 4 centimeters. The overall guideline for the selection of number of armature slots given in the next slide. So here it is the number of selection of armatures with different parameters. First parameter is slot pitch pi d upon s, that should be between 2 to 4 centimeters. Slot loading I that it should be less than 1500. For good combination, slot per pole should be between 9 to 16, and to reduce to flux pulsation, slot per pole that should be integer plus half, and slot per pole arc should be integer, and number of conductors per slot z equal to z upon s should be even integer, and number of turns per coil, the number of conductor per slot divided by number of coils, that should be even integer. And for lap winding, number of slots s equal to should be multiple of pole pair, and the number of wave for the wave winding, number of slots should not be multiple of pole pair, and current density should be at around 4.5 to 7 ampere per millimeter square, and pitch of the commutator segment should be between 4 to 9 mm. Now coming to dimension of armature conductor, so armature current we can say I A equal to PA into 10 power 3 by E, and where IA equal to IL plus IF for generator and I equal to IL minus IF for motor. So conductor current is IZ equal to I upon A. So area of the cross section of conductor A equal to IZ upon sigma, where sigma is the current density, and area of the dimension of armature conductor, that the area of conductor is AZ equal to IZ upon del. So value of the current density are as for. So we use the large machine with a good ventilation. So current density can be as high as like a typically 4.5, and large machine with normal ventilation out of 5, and the fairly high ventilating machine 6 to 7. Now dimension of armature conductor, the enameled coated round wires of cross section up to 10 millimeter squares are used for a small machine. Rectangular or square conductors are used with the cotton on enameled covering for cross section about 10 millimeter square, and the cross sectional area is limited to 50 millimeter square because of eddy current loss in the conductor. So if it exceeds 50 millimeter square, the laminated conductors or standard conductors are to be used, and when the frequency is less than 25, the depth of the single conductor is limited to 19 millimeter. So now coming to slot dimension, as you can see in the typically in the diagram, the cross section of slot is represented in the adjacent figure. Here A is equal to WS into DS, and typically W are the width of the slot and width and depth of the slot respectively, and the slot dimensions should be so chosen that the required number of conductor can be accommodated with the sufficient insulation. Now coming to depth of armature core as in the shown the diagram. So armature core flux is represented as flux in armature core is flux per pole by 2. The flux density armature core BC equal to pi by 2 divided by area of the armature core, so that is pi by 2 DC into Li. So where DC is the depth of the armature core and Li is the typically core length. Now coming to depth, this armature flux density in the armature core can vary between 1 to 1.4 Tesla. Assuming suitable value of BC DC can be determined, and here diameter of armature core will be Di equal to D minus 2 DS plus DC, where DS is the depth of the slot and DC is the depth of the core. Now coming to determinants of armature resistance, so the length of mean turn of armature winding in millimeter will be LMT equal to 2 L plus 2.3 tau P plus 5 DS. So where Li is the core length, TP is the slot pitch, DS is the pure depth of the slot. Hence the resistance per conductor will be half rho LMT by A, where A is the area of armature core. So resistance of each conductor is half Z upon A into rho LMT by A. and total distance for armature will be 1 upon A into half into Z upon A into rho LMT upon A. Now coming to design of commutator and brushes, as you can see in the photogram how bush and commutator looks like. So segments of commutators are made of hard drawn copper and are separated from each other by thin strip of mica or micanite, and diameter of the commutator is between 0.6 and 0.8 times that of armature diameter, with the peripheral speed about 15 meter per second. So distance between the brushes spindle may be taken as 25 to 30 centimeter for a 500 volt machine. The number of commutator segments is equal to the number of coils. So the length of the commutator is decided by the space required for brushes, number of brushes per arm, and area required to dissipate heat generated by the commutator losses. So now coming to the total number of commutator segment equal to number of coils, that is C equal to half US, where U is the number of coils side per slot and AC is the number of slot, and the minimum number of segments to give the voltage of 15 volt between segment at no load, that is C minimum EP upon 15. So E is the induced EMF in armature, P is the number of poles. So we can say length of commutator in millimeter will be LC equal to NB in bracket WP plus CB plus C, where NB is the number of brushes, W is the width of the brush, CB is the clearance between the brushes, and choose in the range of 3 to 5 centimeters. C is the clearance between staggering of the brushes and clearance at end, and chosen in the range of 15 to 40 millimeter. The overall length of the commutator LC equal to LC plus 20 millimeter for riser. Now coming to brush dimensioning, the number of brush arm in machine is equal to number of poles. So there may be more than one brush in brush arm, as it is decided by the maximum current, and the collection of brushes in one arm is called brush spindle, as they have same polarity, as you can see typically here in diagram. So the current carried by the brush arm is IB equal to 2I upon P, where current density in this is 16 to 15 ampere per millimeter square. And total brush area per arm is AP equal to 2I upon P sigma B, where WB, TB are the width and thickness of brush. So now coming to losses in commutator losses. The losses in commutator are due to the brush friction loss and brush contact. So brush friction loss equal to PB equal to mu PB AB VC into 981 10 to the power minus 5, where mu is the coefficient of friction ranging from 0.12 to 0.3. PB is the brush pressure on commutator ranges from 100 to 150 gram per centimeter square, and AB is the contact area of all brushes in centimeter square, and we see the peripheral speed of commutator in meter per second, that is pi dc into n. So brush contact loss is equal to PBC, that is brush voltage drop per brush set into the armature current, that is PB IA. So now coming to typical commutator loss calculation with the brush contact for different material. If you have a natural graphite, the brush contact voltage drop is 0.7 to 1.2, current density is 0.1 ampere per meter square. So pressure is 14 kilonewton per meter square, and commutator speed is 50 to 60. So friction coefficient will be 0.1 to 0.2. Similarly, you can see for all the material. Coming to metal graphite, that is you have a brush drop 0.4 to 0.7 volt, and the current density 0.1 to 0.2 ampere per meter square, and pressure is 18 to 21 kilonewton per meter square, and the commutator speed is 20 to 30 meter per second, and coefficient of friction will be 0.1 to 0.2. So now coming to temperature rise of commutator. Commutator temperature is calculated total commutator loss PBC plus PBT, where commutator cooling surface is pi dc into LC. So DC commutator diameter, that is 0.6 to 0.8 into D, and LC is the length of commutator. So temperature rise will be PBC plus PBT, that is the total loss in commutator into cooling coefficient divided by pi D into LC. Now coming to design example 2 with the commutator and brush design. So question is design suitable commutator and brush for an 850 kilowatt 440 10 pole 300 rpm DC machine. The armature diameter is 150 centimeter with 450 coil, and commutator is to be designed with the commutator diameter equal to the 0.6 times armature diameter. The peripheral speed of a commutator must be greater than 16 meter per second, with the commutator pitch less than 7 millimeter, and take the current density in the brushes to be equal to 6.5 ampere per centimeter, with the brush current greater than 65 ampere, a voltage drop brush voltage of 2 volt, and the brush pressure is 1250 kg per meter. Now solution is the power is given 850 kilowatt, voltage is 440, P equal to 10, N equal to 300 RPM, D equal to 150 centimeter, C equal to 450, D is equal to 0.6 D, V equal to 16 meter per second, sigma is 6.5 ampere per meter square, and I is greater than 65 volt, brush voltage is 2 volt, PV equal to 1250 kg. We know the commutator diameter D is equal to 0.6 D, so D is equal to 0.6, that becomes like 90 centimeter, and peripheral speed of the commutator is V is equal to pi DC, and it becomes 1417 centimeter per second, so it becomes 14.13 meter per second. Now number of commutator segment is 450, so pitch of commutator segment, that is B is equal to pi DC upon C, so it becomes 6.28 millimeter, is less than 7 centimeter, so as given limit, so armature current I equal to Q upon B, that becomes like 1931.8 ampere. If lap wound machine is used, so current per brush will be 2I upon P, that becomes 383.36 ampere, and if the brush current is 65 ampere, as per the limit specified in the problem, the number of brushes per arm will be equal to NB equal to current per brush divided by brush current, so 386.36 divided by 65, it becomes 6. So new brush current IB equal to current per brush divided by per arm, so it becomes 64.39, and contact area per brush will be IB into sigma, so it becomes 9.9 centimeter square. Now the brush should not cover more than 3 commutator segments, so brush thickness is 3 into commutator pitch, that is your typically into 3 into 6.2, so 18.86, that's around 20 centimeter, taking brush thickness of 20 millimeter or 2 centimeter. So brush width is your W equal to AB upon TB, so it comes 4.95 centimeter. So take a 0.5 as a clearance between brushes, so 4 centimeter for staggering of the brushes and clearances. So length of commutator LC equal to NB, WB plus CB plus C, that becomes 36.7 centimeter. So brush contact loss PHC will be 2IA and 2IA, that is 36.6 watt, and contact area per one brush WPW, that's 4.95 into 9.9 centimeter square. So brush fraction loss is PBF equal to mu B PB AB VC into 981 10 power minus 3. So putting all these values, it comes PBF equal to 24713.48 watt. Total commutator loss adding the PSC and PAB, it becomes 28.577 kilowatt, and cooling surface area pi DC, so that is pi d into 1913, so it becomes 1.09 meter square. So temperature rise will be like your 120 loss per watt per centimeter divided by 1.01 C4 of cooling because of the peripheral speed. So putting the value, it comes 136.91 Celsius. Now coming to as a design example 3 for the armature design. So we can say the exam with the design example third, the question, determine the armature diameter, core length, number of armature slot, armature conductor and commutator segment for 350 kilowatt, for 40 volt, 720 RPM, 6 pole 6 DC generator. The average flux density is 0.161 Tesla. Output coefficient is 163. Assume a square pole face with the ratio of pole arc to pole pitch equal to 0.66, and the full load efficiency is 0.91, and the internal drop is 4% of the radius, and diameter of the conductor is 0.7 of armature diameter. The voltage between the adjacent segments will not exceed 15 volt at no load. So now coming to the solution, power developed is P equal to your output power divided by efficiency, 385 become 385, and speed is n equal to RPM upon 60, 12 RPS, and D square L will be P upon CO, and so it comes 0.198 meter cube. For square base, L equal to pi psi tau, so L becomes typically putting a value 0.345 D, and putting the value in output equation, 0.345 D cube equal to 0.198, so D becomes 0.835 meter, and the L is 0.29 meter. So now flux per pole is equal to B average pi DL upon P. Putting a value, it becomes 77.3 millimeter Weber, and generator voltage is equal to your V plus IR, so it will be 457 typically 0.6 volt, and number of armature conductor Z equal to E upon pi P phi N. So putting a value, it becomes 493. So number of slots which varies from 25 to millimeter to 35 millimeter. Therefore, number of slots lie between pi d upon this slot pitch, so it will be 73, and pi d upon it becomes your typically 102. So number of slot per pole should lie between 9 to 16 port proper combination. Thus the range of the slot lie between 73 to 96. So in for number of slots in lap winding, so typically the number of slots should be multiple of the pole pairs. So if it is desirable that number of slot per pole is integer plus half, so therefore number of slot should be odd number, which is multiple of p by 3, that is 3, and choice can be made from 75, 81 or 87 and 93. So to reduce the pulsation, number of slots per pole should be as integer plus half. So with 87, s equal to 87, number of slots per pole are is nearly around integer plus half. So now coming to number of slots equal to psi s upon p, putting value it becomes 9.57. So to reduce the pulsation, s equal to 97 slot is selected, and the winding typically in order that the voltage between resistors should not exceed more than 15 volt at no load. So minimum number of coils equal to EP upon 15. That is 176, and conductor per slot should be Z equal to Z upon S. It's say 5.67. Now coming to the number of conductor per slot should not be an even integer. So Z equal to should be an even integer. So it's Z is equal to 6. So number of conductor used is 6 into 87, 522. So only 5.88% change in calculated conductor. That is 522, and switch conductor is 493. So now the coil side per slot is equal to half mu s, putting a value it comes 86 equal to 87. So with the slot S87, so coil becomes like a half mu s, that's a 174 and or 252. So minimum number of coils is 176, and therefore mu equal to 2 cannot be used. The result with a small number of coils, so mu equal to 4, the number of conductor per slot are not divisible by the number of coil side cannot be used. Solution is equal to 252, and the number of commutator segment is 190. So now diameter of commutator segment, it becomes T is equal to 0.7 D, it becomes 0.585, and C52 P of the segment is beta C pi D C upon C, so it becomes 7.3 millimeter. So hence the design with the S equal to 87 is used. Now coming to design of field system. So this section describes about the type, height and area of poles along with the design of field winding. So design of poles and field winding include the calculation of area of cross section of poles, height of pole, yoke, and design of the series and field windings. So coming to first as a design of pole. So considering the area of the poles, the area of the poles are laminated and are bolted to the frame. So total flux in the pole is pi p equal to usual flux plus leakage flux. So that is pi plus pi L, where the value of leakage flux for the different range of machine is given here. So if you have a machine of 50 kilowatt, the leakage coefficient is 1.125 to 1.22, and if it is a 2 megawatt machine or 2000 kilowatt, that's a 1.06 to 1.12. Now for the area of the pole, the flux density of the pole body can be assumed between 1 Tesla to 1.7 Tesla for limited pole. So area of the pole body is AP equal to pi p upon pp, or AP gross will be AP upon 0.95, where 0.95 is the stacking factor for laminated structure. To avoid the magnetic centering and to allow the end plate, the length of the pole is made less than length of the armature, that is by 10 to 15 millimeter, that is LP equal to L minus 0.001 to 0.15. And now typically area of the pole's width of the pole body is WP equal to AP upon LP, that is pi p upon BP into LP. As you can see the dimensions of the pole body of pole 2. So however, the for machine using limited core for pole, the area axial length of the pole is equal to that of the armature core, and therefore LPI equal to Li. So now coming to height of the pole. To find out the height of the pole, the field EMF to be provided by the pole at full load has to be determined. So this is calculated from magnetization characteristics of the machine. So height of the pole is decided based on first is the sufficient space for series, shunt and both field coils, and cooling surface of the dissipating the losses. So full load EMF and height of the pole are related with each other, and anyone can see estimated only when one of them is known. So now coming to design of field winding, let's consider the cylindrical coils and neglecting the cooling surface of the top and bottom. The cooling surface area of the field winding is S equal to 12 MT into HF. and where LMT is the length of mean-turns of the field winding and HF is the height of the field winding, and let P be the permissible copper loss in each field coil, that is total permissible loss, that is 2 LMT HF into QF, where QF is a permissible loss per unit winding surface for normal temperature rise in watt per meter square. So now coming to the sectional area of field winding coil is HF into DF, and actual copper in the each coil is KF DF into HF into DF, and where KF is the winding space factor having a value of between 0.4 to 0.65 for round coil and 0.75 to 0.8 for rectangular conductor. But the area of the copper in the field coil can also be TF into FF. So where TF is the number of turns in field coil, F is the sectional area of the field conductor in meter per square. So TF into FF will be KF into HF into DF. So now you can say copper loss in the field coil is QF equal to I square IF square RF, that is IF square TF into rho into LMT upon FF, and or FF sigma square TF sig rho into LMT upon FF, or sigma square TF rho LMT into F. So now coming to volume of the copper in each field coil, that is sectional area into length of mean turn into number of turns. So that is F LMT into TF. The copper loss in each field coil will be QF equal to rho square sigma rho square rho into volume of copper, and from this two equation we can get QF equal to sigma square into rho LMT KF HF TF. So copper loss will not exceed the permissible limit of copper, hence 2 LMT HF QF equal to sigma square rho LMT KF HF into DF, and or you can call it rho F equal to under root 2 QF upon rho KF DF, where QF is the rho F is the current density, that's 3 ampere per millimeter square. So MF per meter height of the field winding ATFL upon HF, or IFTF upon HL, or sigma FF into TF upon HF. So now using the value of HF FFTF, the MF meter per height of the field winding, that is sigma F into KF HFTF upon HF, that is equal to sigma F into KF TF, or equal to KF DF into under root 2 QF sigma KF DF, or equal to under root 2 QF KF DF upon rho. So considering the resistivity of the copper 2 into 10 power minus 4 ohm meter and QF in watt per meter square, DF is in meter. So height of the field winding will be HF equal to 80 FL into 10 minus 4 under root QF KF DF, and total height of the pole will be HV will be equal to HF plus height of the pole soup plus height of the insulation and height of the wastage due to the curvature of the yoke. So now coming to typically the for the different diameters of armature, we have field winding width. If you have a 20 centimeter diameter of armature, so normally winding depth is taken 3 centimeter. If it is like your 100 centimeter armature diameter, then it is normally 5.5 millimeter. That's the depth of the field winding. Now coming to design of shunt field winding. The shunt field winding is designed generally to produce rated voltage at no load in shunt and compound machine, where the series field winding is designed to maintain rated voltage at all the load. So the general design procedure for design of shunt field winding is given here. To find the total height available on pole for both the field winding using height of in field coil, that is HF equal to ATF upon 80 per unit height, and design of shunt field winding is for compound machine, height of the shunt field winding LHS equal to 80% HF, height of the series field winding and HS is equal to 20% HF. So for shunt machine HS equal to HF. The number of shunt field coil will be number of poles. Assuming 15 to 20% of the rated voltage is lost in the field regulator, the voltage across the each one field will be F equal to 0.8 to 0.85 V divided by P, and E where V is the rated voltage and for shunt coil are connected in series. And coming to step 4, calculate the length of mean turn of the field, that is LMT equal to 2 LP plus BP plus 4 DF, and we know the resistance of each coil is RF EF upon IF, that is rho LMT TF upon A, and area of the typically field coil will be F equal to rho LMT TF upon RF, or rho LMT TF IF upon EF, or rho LMT ATF upon EF. Now fifth step is choose suitable sections depending on the size of the machine and select the suitable thickness of the insulation. So now coming to the typical number of the conductor per depth wise, and equal to DF upon depth of the one insulated conductor, and the number of conductor per height NH will be HF one height of one insulated conductor. So adjust ND and H needs to be whole number or integer. So TF equal to ND into NH. For this, TF and AF, you should find RF equal to rho LMT upon AF, that is IF equal to AF upon RF, and check for the current density. So sigma F will be IF upon IF, that should be less than 2.5 ampere per millimeter square. So if air ducts are provided, it can be taken, sigma should be less than 3.5 ampere per millimeter square. Now coming to the next step to design of shunt field winding, find IFTF. If IFTF is given value, then the calculate the copper loss I square IFRF, and if else it IFTF is given value, then increase the DF also the IFTF given value, decrease the DF and go to step 4 and find the cooling surface S equal to LMT HF DF plus DF, and then temperature rise equal to theta equal to 120 into loss in watt per centimeter divided by 1.1 plus 0.1 Vc, and if theta is less than 40 degrees Celsius, design of field winding procedure complete. Else increase the surface area by increasing the DF and go to step 4. Now coming to design of series field winding, the series field winding has ampere turn equal to pole as 10 to 20% of armature ampere turns on full load. So ATSC equal to 10 to 20% of ATSC in compound machine. So it's ISC equal to IA or TSC equal to ATSC upon SC, and area of cross section area in series field winding will be SC equal to I upon sigma SC. Sigma SC current density in series field winding. So current density in case of series field winding can be taken slightly more than the shunt field winding. Now coming to design of interpole winding. So the interpole winding design, the current in armature winding of DC machine changes if direction of the armature changes in alternate this. So commuters converts the alternating current into unidirectional current. So current is collected from the buses, covered 2 to 3 segment of commutator. So brush short circuit the coil in which the current reversal take place from plus IC to minus IC or vice versa. So this change of current is opposed by self-induced EMF in the coil called reactive voltage or reactance voltage, and if the coil going under commutation to reverse the current, a reverse induced EMF has to be developed which is sufficient to overcome the reactance voltage drop, and this reverse EMF is provided by interpoles or compoles located between the two consecutive main poles. So these poles carry a winding called compensating winding connected in series with the armature and are excited to provide a field required strength and polarity. Generally, machines will have interpoles of polarity same as that of main pole ahead, and in motoring machine will always a polarity interpole same as that of pole behind in the same direction. So the armature turns required interpole must be sufficient enough to neutralize the armature action and to overcome reactance voltage drop due to commutation. The MF due to armature action without compensating is AT equal to IZ upon 2P, and IMF due to armature action with compensating winding, that is AT equal to IZ upon Z upon 2 pi minus pole arc upon pole pitch, because in pole arc only we are putting the compensating winding. So I have required for flux density in the air gap at interpole 800,000 into VGI into KGI into LI, where LGI is equal to 1.5 to 1.75 LG, and MF required for interpole ITP 800,000 to VGI, KGI, LGI plus ATA. So MF required in the air gap for interpole 800,000 BGI, KGI, LGI, where LGI is 1.5 to 1.75 LG. MF required for interpole is ATIP equal to 800,000 BGI, KGI, LI and plus ATA. So width of the interpole equal to distance between which the armature move during competition. WI equal to width brush thickness plus n minus 1 pitch of the commuter segment, that plus dA upon dC. So where the n dash is the number of coils sides per layer in the slot, and dA is the diameter of the armature, and dC is the diameter of commutator periphery. So reactance voltage can be calculated by calculating the permeance of slot, tooth pitch and overhang. Permeance of the slot is lambda is equal to H1 3WS plus H2 WS plus 2H3 WS plus W0 plus H4 W0, and permeance of coefficient of tooth will be lambda T equal to Wi upon 6 Lg. So permeance coefficient of overhang is lambda 0 equal to Lm LTR upon L in bracket 0.23 log 10 tell TR upon B plus 0.07, and LTR is the free length of the overhang and B is the periphery of one complete layer of the winding. So total coefficient permeance is lambda equal to lambda S plus lambda T plus lambda 0. The effective leakage flux for a slot with Z as conductor carrying the IZ current will be MF divided by slot into M into permeance coefficient into length, that is IZ into ZS into mu into lambda L. And since there are two coils, so total flux limit will be 2 into mu lambda L IZ So interpole are made to cut steel with the no pole. So total flux density in the interpole is BGI equal to mu 0 lambda Li ZS upon Li into Wi, and number of interpole turns in TIL equal to ATI upon IA. So current density interpole winding 2 to 4 ampere per millimeter square. So average value of the reactance, that ER average L di by dt 2 T square L lambda 2 L Z upon Tc, and the Tc the time of the commutation. If the thickness of brush is equal to 1 computer second, then Tc equal to pi dl upon C into pi dl into n. So it becomes 1 upon Cn. And substituting Tc in E average, we get the EV average equal to 2C square lambda L lambda 2IZ Cn. And rearranging the above equation, we can get average equal to 2Tc L lambda Z 2C Tc n, and substituting 2C Tc equal to Z in the above equation, multiplying dividing by pi d. So E average is 2 Tc lambda L lambda in bracket IZZ upon pi d into pi dn, and it becomes 2 Tc into L lambda dash AC into V. Now coming to losses and efficiency in DC machine. So losses in DC machine can be classified into two types: rotational loss and I square loss. And rotational loss, there are made of friction windage losses, and second is iron loss. And friction and windage loss, the friction losses occur in bearing and at the commutator. The amount of the bearing losses depends upon the pressure on the bearing, the peripheral speed of the shaft, and the bearing of the coefficient of the friction between the bearing and the shaft. And friction losses in commutator due to the brush contact can be calculated PBF mu B mu PB into VC, where we see the peripheral speed of commutator in meter per second, PV the brush contact pressure on commutator in Newton per meter square, and AB the PAB total contact area of the all brushes in meter square, and mu equal to coefficient of friction. Now coming to the friction and windage loss calculation, the windage losses produced by the rotational depends upon the peripheral speed of the rotor and rotor ammeter and core length, and largely upon the construction of the machine. And the windage loss in fact depends upon the too many integrate factors and cannot be easily assessed. So adjustment table give the value of windage plus bearing and friction losses experienced as a percentage of. So you can say depends on peripheral speed like a 10 meter per second. So your losses percentage of the output is 0.2%. If you go to the peripheral speed 50 meter per second, it's a 1.2% of the output power as a bearing friction windage loss. Now coming to iron losses, the iron loss per kg is given by following, since that is a 0.006 FBM square plus 0.008 F square BM T square for teeth of the machine, and 0.06 FBM square plus 0.005 F square BM T square for 4 type of the machine, teeth of machine, and for core of the machine. So the pulsation loss in the pole phase may be taken as a 20 to 50% of the total iron loss as calculated above. So iron loss occurs in mainly main series circuit of armature. This includes I square loss in the armature winding, that is I square RA, interpole winding I square RP, series field winding IA square RF, compensating winding IA square RC, and brush contact PBC. So compensating winding is normally not present in all the machines. Series field winding is present only in compound machine. So shunt field circuit, these losses include the I square losses in the winding itself and also I square loss in the field regulator. Now coming to straight load losses. So these are certain types of losses which appear when the machine is loaded, and these may be possible reasons for straight load losses. There is a large increase in the iron losses when the machine is loaded due to the distortion of the field caused by the armature reaction, and due to eddy currents in conductor there is a additional I square losses, and when the coil goes under commutation this is circulated by the brush, so this causes circulate current to flow which produces additional losses. The straight load loss may be assumed 0.5 to 1% of the basic output of 4 machines with and without compensating winding respectively, and basic output is the power which correspond to maximum current at the highest rated voltage for constant speed characteristic. The efficiency percentage efficiency will be eta equal to output power divided by output plus losses or 1 minus losses upon input. The condition for maximum efficiency in case of constant speed and constant voltage is constant losses PO. These losses do not vary with if the load current varies. So for a shunt machine, the losses are bearing plus frictional losses, brush friction loss, shunt excitation losses, and no load iron loss. And losses proportional to I square armature current. Even that is these losses vary linearly if the load current varies, and brush contact loss. And losses proportional to square of the armature current P2. These losses vary as the square of armature current, that is I square loss. This in the armature and history load losses. Now coming to efficiency, the total losses are PL equal to P0 plus P1 plus P2, and the first approximation can be expressed in the form like PL equal to K0 plus K1I plus K2I square, and I denotes the total current drawn from by the armature of the machine. You can see in the diagram how the variation of different losses are there typically. So now in order to simplify the analysis, total current drawn by the motor is assumed I, and motor input power is therefore VI. The efficiency, for efficiency, we can say PL equal to K0 plus K1I plus K2I square, and efficiency 1 minus K0 plus K1I plus K2I square divided by VI. That is equal to 1 minus K0 upon I plus K1 plus K2I, where K0, capital K0 is small k0 upon v, and k1 is small k1 upon v, and k2 equal to small k2 upon v. Now in order to find out the maximum efficiency, this eta is differentiated with respect to I, and then should be equal to 0. So that makes delta eta upon delta x minus k0 I square plus k2 equal to 0, or k0 equal to k2 I square. For maximum efficiency, it results like constant losses equal to losses proportional to the square of current. Now coming to temperature rise. The temperature rise of the armature the step 1, the cooling coefficient are taken from the table for particular machine. Typically for cylindrical DC machine, it is cooling coefficient 0.015 to 0.035 divided by 1 plus 0.1 V, and for commutator it is 0.015 to 0.25 divided by 1 plus 0.1 V, where V is the peripheral speed. Now coming to temperature rise of the armature, the step 2, the cooling coefficient numerator has been selected, say 0.03. Now the losses dissipation from each surface is calculated. For example, the outer cylinder surface area of core is pi d0L, and the loss dissipated from the back exterior core is in bracket pi d0L divided by cooling coefficient N R. And similarly, the loss dissipated from inner surface pi dl, area of the end surface including the pi bracket d0 square minus d square by 4, and duct are calculated, and total loss dissipated is the sum of all the losses. So now as a step 3, the total loss to be dissipated equal to copper loss in slot portion of conductor plus iron loss. So therefore average temperature at theta equal to total loss to be dissipated copper plus iron losses in watt divided by total loss dissipation watt plus or Celsius degree, and comes in degree Celsius. So temperature rise in the armature can be estimated from the empirical formula given as theta equal to 250 to 350 P dash divided by 1 plus 0.09 VA to power 1.3, where P is the total armature copper loss and iron loss per square centimeter of the cooling surface in watt per centimeter cube, and VA is the peripheral speed of the armature in meter per second. Now coming to as a design example 4, as a performance calculation of DC motor. Question is, calculate the performance with respect to iron losses, armature copper losses, temperature rise in the design armature of 500 kilowatt for 4375 rpm 8-pole lap wound DC generator, whose various design information are given here. External diameter of armature 1.1 meter, cross length of armature equal to 0.3 meter, and useful flux per pole equal to 0.0882 Weber. Dimension of slot is 8 mm into 43 mm, maximum flux density 2 Tesla, sectional area of all the teeth per pole 0.068 mm square, and RPH is 0.008 ohm. Constant A for the armature core is 0.0045, and constant A for teeth is 0.007. Now coming to as iron losses in the armature, the flux in the core section is phi equal to half of pi, that is 0.082 upon 2 equal to 0.0441 Weber, and flux density in the core is 1.3 Tesla, and area of the armature core JC equal to this flux divided by flux density is come 0.0339 meter square. Now coming to assuming 4 ventilating duct in 1 centimeter wide and the iron factor of 0.9. Now iron length of the armature core is Li equal to 0.3 minus 4 into 0.01 into 0.9, that is 0.234 meter, and depth of the core below the slot DC, that is typically calculating from the this comes 0.145 meter, and mean diameter of the armature core d MC equal to d minus 2HS minus DC, putting a value it comes 0.869 meter. Now volume of the core is keeping a value, in this it comes 0.0923 meter cube, and weight of the iron multiplying it by density it comes 722 kg, and frequency of flux level is 25 Hz. So stage load per kg at 1.3 Tesla and 25 Hz is 2.4 watt, and the stage loss in armature core 2.5 into 722, that is 1733 watt. Now eddy current loss per kg in the core is A PCF T square in watt, and putting value it comes 1.2. Eddy current loss in core it comes multiplying the weight it 866 watt. So total iron loss in the core comes by addition of 2599 watt. Now iron loss in the teeth, area of the all teeth per pole is 0.0638 meter square, and area of the teeth on the armature is 0.0638 into 8, that is 0.51 meter cube, and volume of all teeth is multiplying this area into the typically the density comes to 1930 centimeter cube, and multiplying the density comes 171 kg. So stage loss per kg at 2 Tesla at 25 Hz 6.4 watt, and the stage loss in this is 6.4 into the weight 171 kg, that comes 1094 watt, and the current loss in kg in the teeth is A equal to A BC F T square watt in watt, and putting value it comes 4.38 watt, and eddy current loss in the armature teeth finally multiplying the weight it comes 749 watt, and loss in the armature teeth adding both it comes 1843, and total iron loss in teeth adding further with that it comes 4442 watt. The armature copper loss, the resistance of the armature winding 0.008 ohm, and full load current is power divided by voltage it comes 1136 ampere. Thus the armature copper loss I square RA it comes 10,324 watt. So temperature rise in the armature is theta equal to 250 to 350 B dash divided by 1 plus 0.09 VA 1.3, and where VA peripheral AC pi d and 160 it comes 21.6 meter per second. Total armature loss is addition 4.44 plus 10.32 plus straight load losses. So straight loss assume 25% of total iron loss. So total iron loss by adding all value it comes 15.88 watt. The whole length of armature is L plus of overhang of the winding. So putting the value here it comes typically 50 centimeter. So now total armature copper loss per square centimeter of cooling surface P dash equal to total armature loss divided by cooling surface of the cooling value it comes 0.92 watt per centimeter square. So temperature rise of armature theta equal to, putting in formula it comes 43 degrees Celsius. Now coming theoretical problems. Question 1, mica is used in the insulation of commutator segment because it has mechanical strength, has a very high specific weight, as a D option. So write down the factor governing the number of poles. Answer is factor governing the number of poles are frequency of flux reversal, weight of iron parts, weight of copper, overall size of machine, commutator length, flash over between the brushes, labor charges. And question 3, what is the main reason for sparking at the brushes in the DC machine? Presence of reactance voltage in the main cause of sparking at the brushes in DC machine. And question 4, how interpole DC machine are used to achieve spark-like commutation? Answer, design of interpole is done in order to induce an EMF in the short circuit coil undergoing commutation to oppose the and utilize the reactance voltage, but in itself exploring spark-like commutation. Question 5, what is the minimum number of slots per pole used in design of DC machine to minimize sparking of commutator? Number of poles slot per pole should not be less than 9 so as to minimize the sparking in the commutator segment. Question 6, mention the factor that decide the minimum number of armature coils in DC machine. Maximum voltage between the adjacent components decide the minimum number of the coils in DC machine. Question 7, what are the conditions to deciding the choice of the number of slots for a large DC machine? Answer is factor deciding the number of slots for large DC machine is slot loading should be less than 1500 ampere conductor, and number of the slots per pole should be greater than 9 in order to avoid sparking, and the slot pitch should lie between 25 to 35 millimeter. Question 8. What is the slot loading? The slot loading is the product of current in the armature conductor and number of the conductor per slot. That slot loading into IZ into ZS in ampere conductor. Mention the location of commutator in DC machine. Answer: commutator is placed midway between the main poles of DC machine. Question 10 is why the brushes are staggered in DC machine. The brush answer is that brushes in DC machine are staggered. The brushes are staggered in DC machine so as to prevent the grooving and damage to the commutator, and staggering of the brushes is displaying the positive brush sets in one direction and negative brush other direction, and this ensures uniform bearing of commutator segment of our surface and avoid the step between the brush sets. Now coming to numerical problem. Question 1. The diameter and length of a 1200 kilowatt 500 volt 300 rpm DC machine is 1.45 meter and 0.35 meters respectively. Calculating the mean EMF per conductor, total flux and number of the conductor connected in series, and armature drop is 6.5 volt at full load, and maximum flux density in the air gap is 1.101 Tesla. Given solution, given P equal to 1200 kilowatt, voltage is 500 volt and 300 rpm, and D is 1.45 meter and L is 0.36 meter. Armature drop is 6.5 volt and BG in 1.01 Tesla. So where B average equal to BG into form factor, putting a value, it comes 0.707 Tesla. Speed in RPS is RPM upon 60, that comes 5 RPS. And now mean EMF per conductor is BALV, so putting value, it comes 5.79, and total flux is B average 5DL, that comes 1.15 Weber. Now induced EMF at full load is equal to V plus IRA, putting a value, it comes 506.5 volt. Number of conductor in series, induced voltage EMF on load, and induced EMF divided by conductor, putting a value, it comes 88. Now coming to question 2. A 4-pole DC motor draws the current of 160 ampere. It has 480 armature conductor wave winding A and B lap winding. The brushes are given an actual lead of 10 degree. Calculate the cross and dividing EMF per pole. In each case, the field winding is shunt connected and takes a current of 10 ampere. Find the number of extra shunt field turns to neutralize the demagnetization. So solution for the wave connected, I equal to 160 minus 10, that is 150 ampere, and with the wave number of parallel path equal to 2, and armature EMF per pole is 80 equal to IAZ upon 2 PA. So putting values come 4500 ampere, and angle lead alpha equal to P by 2 theta mechanical, so it comes 20 degrees electrical, and demagnetization of 80 AD equal to 80 into 12 upon 180, it comes 1000 ampere. Now the cross magnetizing 80 equal to 80 minus 80D, that comes 3500 ampere, and for neutralizing EMF is 1000. So extra turns required from the shunt field for wave connection, 1000 upon 10, that is 100. And for B, for lap connected, the wave winding number for lap winding, the number of parallel path equal to 4, and armature EMF is 80 equal to IZ to 1A, so it comes 2250. Angle of lead is alpha equal to P by 2 theta mechanical 20 degree. Demagnetization of 80D equal to putting a value 500 M, and the cross magnetizing 80 equal to 80 minus 80, so it comes 1750. And I have neutralizing demagnetizing 500. The extra turns required to shunt field for lap connection 500 by 10, that is 50. Now coming to question 3. A 100 kilovolt 500 volt 6 pole 450 rpm DC shunt motor has the following data. The armature diameter of equal to 0.54 meter, pole length 0.245 meter, average flux density in the air gap is 0.55 Tesla, number of ducts 2, width of each duct 10 millimeter, stake factor of 0.92. Find the number of armature slot and work out the details of a suitable armature winding. Also work out the dimension of the slot. The flux density is at 1/3 height from the root of not exceed 2.1 Tesla, assuming the full load efficiency of 0.89, and armature voltage drop of 5% of the rated voltage, and the field current 1% of the line current, and current density of 4.7 ampere per meter. The ratio of the pole arc to pole pitch is 0.66, and check for the following. The slot loading will not greater than 1500 ampere, and a pitch of the the pitch of the commutator segment should not be less than 4 millimeter, and the voltage between adjacent segments should not exceed 15 volt at no load. So now coming to as a solution type of winding, the back EMF is V minus RA, that comes for 75 volt. Line current is P upon this V, it comes 225 ampere, 225 ampere, and field current is 1% of this, that's a 2 ampere. Armature current is now this line current minus field current, that's a 2 to 3 ampere, and armature current is more than 200. The way winding is preferred, that is number of parallel path A equal to 2, and current in parallel path is 232 by 2, that is 115 ampere, is less than 200 ampere. Now number of conductors, typically pole pitch is pi d upon p, that comes 0.283 meter, and flux per pole is B average tau L, that comes 38.2 into 10 power minus 3 Tesla, and speed is your 451.6, that's 7.5 rpm. And number of armature Z equal to putting value in the induced EMF expression will come 553. Now number of slot pitch varies from 25 to 35 millimeter. Therefore, the number of slot lie between the two value between 48 to 68. So number of the slot per pole should be at least 9, and minimum number of slots should be 6 into 9, 54. That's the range in which the number of slot lie 54 and 68. Now in the wave winding, the number of slots should not be multiple of the pole pair. So therefore, in this case, the number of slots should be multiple of 3. The number of slots examined are 54, 57, 60, 63, and 66. The choice can be made from 55, 56, 58, 61, 62, 64, 65, and 60, 67 and 68. To reduce the flux pulsation, the number of slots per pole per hour as integer plus half. So with the S equal to 58 and 67, we obtain the number of slots per pole per hour, the nearly integer plus half. So to reduce the flux pulsation, we must either choose S equal to 58 or 67 from the range of slots. Now coming to the winding, in order to that the voltage between a segment should not exceed 15 volt at no load, the minimum number of coils required C equal to E into P upon 15, it comes 200. The number of slots and coils should be so chosen that there is no appreciable change in the number of conductor provided and the number of conductor calculated. So check with the S equal to 58 and S equal to 67. Now coming with the winding of slot S equal to 58, the conductor per slot is ZS equal to your total conductor by number of slots is 9.56. So number of conductor per slot should be an integer, so Z is equal to 10. The number of conductor used now 10 into 58, 580, and only the 5% change in calculated conductor use 553 and use 580. So now coil side per slot is equal to half into 2 into 58, so it comes 58, and for the case of typically for coil side that comes 116. Now with the winding slot equal with the slot equal to 58, this C comes for U equal to 6, it comes 78. For U equal to 8, it C comes 232, and for U10 it comes 290. So minimum number of coils is 200, and therefore U equal to 2, 4, and 6 can be used, and they result in a smaller coil. So the U equal to 8 or 10 can be used. Now with the U equal to 10 and C 32, then the turns per coil is equal to Z upon 2C. The maximum number not is a mixed number, it is not integer. Therefore U tag cannot be used. With U equal to 10, C equal to the turns per coil is equal to Z1 C is equal to 1. So it's a single turn per coil. So therefore number of slots equal to S58, number of coils 290, and number of conductor Z580, and coil side per slot is 10, and conductor per slot is 10, and turns per coil is equal to 1. Now coming to with the slot equal to 67, conductor per slot is Z is equal to 8.26. So number of conductor slots should be integer. So Z is equal to 8. Number of conductor now use 18 to 67, so it comes 536. So only 3% change in calculated conductor 553 and 580 should be used. Now the coil set per slot for U equal to 2 is comes C equal to 57 and C equal to 132 for U equal to 4, and for U equal to 6 it comes 201, and for U equal to 8 it comes equal to 268, and U10 it comes 335. So minimum number of coils 200, and therefore U2 equal to 2, 4, and 6 cannot be used, and the result are smaller coil size. So the U equal to 8 or 10 can be used. So now taking a U equal to 8 and C 268, then turns per coil is Z CT equal to Z upon 2C, so it comes 1. So therefore U equal to 8 can be used. Now with the U equal to 10, C 235, the turns per coil comes DC equal to Z upon 2C, it's a mixed numbers. So therefore number of slots 67, number of coils 268 and number of conductor Z 536 and coil per side 8 and conductor per slot 8 and turns per coil is equal to 1. Now before finally deciding the number of slots, check for the slot loading. So slotting per conductor is Z equal to 125 with the Z is equal to 10. Slot loading IZ into ZS, putting value it comes to 115 ampere, and with the Z equal to 8 slot opening it comes 892. So slot loading for both the case is below a permissible rate of 1500 ampere. So now coming to commutator segment design, diameter of commutation of DC equal to 0.65 times the typical diameter of the armature, that comes 0.351 millimeter, and with the C equal to 220 pitch segment, beta equal to typically is pi DC upon typical number of the total coils, so it's 3.8 millimeter, and C equal to 58, it comes BC comes 4.1, minimum pitch is segment is 4.1, therefore C 290, and with S 58 and C 220 cannot be used, so therefore design with S 67 is used. Now coming to winding layout, back pitch is YB is 2C plus P plus minus K, so that comes 89, as YB 89 with the YB minus 1 by 2, it is an integer, therefore the commutator pitch Y is equal to C plus minus 1 by P by 2, so it comes 89. So now resultant pitch is Y equal to capital Y equal to Y is 178 and front pitch Y minus capital Y minus B, it's 79. Now coming to slot design, current in each conductor is Z equal to 111.5 ampere, and area of the conductor is AZ equal to I upon J. So taking current density 4.7, it comes 23.8 millimeter square. So is space left for the bar conductor depth wise is slot depth minus the conductor insulation depth wise minus insulation including the lip and weight, it comes 36.1 millimeter. So maximum depth of the conductor there is 18 millimeter, and usually conductor with depth 17 millimeter. The width of each conductor is 23.5 divided by 18, it comes 1.3 millimeter. So space taken by base conductor without 1.3 into 4 is 5.2 millimeter, and space taken by the insulated conductor by putting the value which comes 8 millimeter, as you can see in the diagram. So space taken by the insulation with by 2.5 millimeter, width of the slot is 8.2.5, it comes 10.5 millimeter. So net iron is Li equal to a value of this comes 0.207 meter, and armature diameter at 1/3 height from the narrow end value 0.479 meter, and to get 1/3 height putting a narrow end T by 3, it comes like 1195 into 10 power minus 3 meter. Now flux density in the teeth 1/3 height from the narrow end, it is BTV P5 upon psi SWTLI, that comes 2.06 Tesla. So thus the slot details are bare conductor cross section is 1.3 into 18 millimeter square, and insulated conductor section 2 into 1 18.7 millimeter square. So insulated conductor 2 into 0.7, that comes 37.4 millimeter. Main insulation 3 into 1 3 millimeter, separator 1 millimeter, slack is 1.1 millimeter, wedge and lip 3.5 millimeter, and total slot depth 46 millimeter. Now coming to question 4, calculate the total MF required per pole to produce flux of 0.12 Weber in machine with the following details. The length of the machine is 0.31 millimeter, and the pole arc to pole which ratio is 0.64, and there are 12 slots per pole. The width and height of the tooth are 12 millimeter and 36 millimeter respectively. Length of the flux path between the two ascending pole in core is 0.2 meter. Sectional area of core is 0.038 meter square. Area of the pole face is 0.10 meter square. Length of hair 4.8 millimeter, and sectional area of pole body is 0.076 meter square. Height of the pole is 0.22 meter. Sectional area of yoke is 0.046 meter square. Mean turn length of yoke is 0.43 meter between the two ascending pole, and the relative permeability of the teeth is 88, and for the rest of the magnetic circuit is 1150. Stacking factor is considered 0.92, and lazy flux is neglected. Now coming as a solution, MF for air gap AT delta equal to 5m delta upon mu 0 A delta. So putting a value, it comes for 4585.9 ampere. And MF for pole ATP, it is 5 into HP upon mu 0 mu r. And sectional area of the body, putting value, it comes to 0.5 ampere, and flux in the core, that is 5 upon 2, that is 0.06 Weber. Length of the flux path in core is 0.2 meter. Sectional area comes 0.038 meter square, and MF for ATC, putting a value, it comes to 8.6 ampere, and flux in yoke is 5.2, that's a 0.06 Weber, and length of the flux path in yoke 0.43 meter, and sectional area of yoke is 0.046 meter square. And for yoke is putting value 85 and it comes 388.3 ampere. So now teeth per arc 5 into S upon P, it comes around 8. And now MF 40 30 equal to 0.015 height of the tooth into 88 4 into 10 power minus 7 into stacking factor width of the teeth, length of the machine. So it comes 428 ampere, and total MF is 80 equal to 80 delta plus 80P plus 80C plus 80Y plus 80. It comes 6861.3 ampere. Now coming to unsolved problem. So these are the some of the unsolved problem which you can show on the similar line, and these are the references from which material prepared. And thank you.